What's going on, everybody? How are we doing today? It's dark in here. I don't know why that is. Hopefully you're all doing well. I'm looking a little bummy. Been shoveling the driveway a lot this weekend. Hopefully you all are doing okay as well. Yeah, we're going to be getting started here in just a minute or so once I get all this stuff situated. This is the Unit 6 review for AP Physics 1. We're going to go over some of the rotational dynamics and kinematics concepts from this unit. Now, if this is your first time ever coming to one of these review sessions, then we will, you may be a little confused, but here's how this thing works usually. What I'm going to do here is basically make connections for you, hopefully build some connections in your head before our exam tomorrow, so you have some ideas moving in. So instead of memorizing these concepts, you're able to kind of understand what we've been talking about over the last 3 weeks in terms of rotation. So the big connection I'm going to try to make here today and kind of further, well, I want to make the connection between first semester. All right. I think understanding rotational physics helps when you really understand what's happening first semester. So we're going to kind of draw a lot of connections to Unit 2 and Unit 1, which are forces and kinematics. All right. So that's how we're going to get started. We're going to start by comparing semester 1 to semester 2, and you'll hear me kind of compare 1 to 2 quite a bit. All right. So here we go. And when I'm done going through, if you've got simple questions or questions about what I said specifically, go ahead and throw those in the chat. But if you've got questions on like the review guide and that kind of stuff, I'm going to send you to the key that's most likely posted by your teacher somewhere on their Canvas page. At the very, very end, maybe I'll answer some review guide stuff, but most likely no. Most likely it's just how can I support you moving forward into your exam tomorrow. All right, that's that. Let's get going. So here's what we got for you. Here is our basic comparison. I'm going to get down to my spot. Here's our basic comparison of first semester and second semester. So first semester, we kind of had this phrase, and I said it a lot if you came to the review sessions or if you were in my class. I said our big theme for first semester was outside forces cause accelerations. This phrase we saw to be like to permeate everything we studied, starting in Unit 2, going into circular motion, going into energy and work, going into momentum and impulse, like outside forces causing changes in acceleration was the underlying theme of first semester. Our big equation, if you forget everything else about physics, this is the most important thing to remember from physics, is that the net force acting on an object equals mass times acceleration, right? And this mass term was mass. How much matter makes up something depends or dictates its acceleration when given a net force. Now, second semester, we started with rotation, and we've changed this a little bit. Now, some physics nerds might pull up and be like, well, hang on, Mr. G, like it's still outside forces that cause these torques, so therefore, I get that, right? Like torques definitely are caused by an outside force, kind of, right? So I want to make sure that we are understanding that torques still are forces, but in terms of rotation, if I want to see an angular acceleration, here's how I need to change that phrase. That phrase needs to now be outside torques cause angular acceleration. Our synonyms here, or I guess like our translatable variables here from first semester to rotation, are forces, are basically torques here in rotation, and acceleration is angular acceleration. That's a pretty easy one to catch on to, but forces and torques are very similar. Forces move left, right, up, down, forward, backward. Torques move things around an axis of rotation. Even our net torque expression is strikingly similar. Net torque equals I times alpha. Well, alpha is our angular acceleration. Net torque is is comparable to our net force. So what is this I value? This I value is known as rotational inertia. Okay, rotational inertia is more than mass. It's not just the mass of an object. It's actually how that mass is distributed around the axis of rotation. Every single I value Not every single one. That's okay. I'm overgeneralizing. In our class, for the most part, if we come across something, we're going to see an I equation that is some coefficient times mr squared. Where's that coefficient come from? Calculus. It comes from calculus. It's based on the shape of the object and where the average mass is located. We don't do calculus in this class, so we're not worried about it. All we are worried about is that as the mass gets further and further away from the axis of rotation, that coefficient gets closer and closer to 1. The closer the mass is to the axis of rotation, or the average mass, that number decreases. So for example, a hoop, a very thin hoop, has a coefficient of 1 because all of its mass is as far away from the axis of rotation as possible. But something like a solid sphere, like a billiard ball or a golf ball or a baseball, right? Or a baseball is going to have mass located more near the axis of rotation, and therefore that I value, that coefficient, will be less than 1. This is the basis of rotational dynamics. Let's look at some steady things, some things that aren't rotating. That's where we started. We started with what we call statics. So let's look at some static. One of the static situations that we began with was a hammer on a string. I'm no artist, so don't call me out, but here we go. We had this string, there's the hammer, and I don't know, there's the hammer. That makes sense. Okay, this thing was hung, it was suspended, and it wasn't rotating. It was staying stationary, and I asked us to draw some things about it. Well, let's go ahead, and our first thing we had to do was kind of map out our axis of rotation. As people observing the world, we get to decide where the axis of rotation goes. It doesn't change the physics happening. It just dictates how we do the math. So I'm going to select an axis of rotation at this point right here and then draw my forces acting on it. So there's clearly a tension force here holding the string up. Let's see here. There is like the head of the hammer has an FG over here. The handle has an FG over here. This radius, we can call this radius right side, or R. We can call this radius over here the radius of the left side. But basically, this thing was stationary. And the question I asked you, or you were asked a bunch of times, is like, in order for something to be balanced, in order for it to not rotate, does mass need to be equal on both sides? And in my classroom, I don't know how it went down in your classroom, but in my classroom, I went ahead and took a meter stick and I taped the mass to one side. And I asked my students, as I balanced it, does this need to have equal masses? And some students intuitively were like, yes, it must. So we snapped that meter stick right down where on that balance point and took the mass on both sides. We learned quickly that no, the masses are not equal on both sides for something to be balanced. What we need is our net torque to be 0 newtons times meters. This means we are balanced. This means we are not rotating or accelerating rotationally. This is how we balance. So we can go ahead and write net torque expressions. And we decided that up, down, left, right don't work in terms of directions. For us, we had to use directions like clockwise and counterclockwise in order to understand this. So our forces acting away from the axis of rotation, like the force of gravity on the left side and the force of gravity on the right side, produce these torques. So we can say that the force of gravity on the right side is pulling down around the axis of rotation, causing a counterclockwise torque. I don't know about you. I mix up my directions all the time. So I just always say it's one direction minus the other direction. So that's what we're going to do. I'm going to say that the torque of FG left minus the torque of FG right, because they're in opposite directions. So I made left, or the counterclockwise direction, positive, the clockwise direction negative. These two things should be equal to each other. And what that means for us, and we can prove this mathematically if we're asked to, M on the left side times R on the left side minus M on the right side, R on the right side, are equal, right? These two things are equal. Therefore, if there's a larger radius, as radius goes up on the right side, mass goes down on the right side. And as the radius goes down on the left side, the mass goes up. So our masses do not have to be equal in order for something to be in rotational equilibrium. Their torques need to be equal and opposite in direction, but their masses certainly do not need to be equal. All right. Another example we saw was the seesaw. The seesaw example where we had a long beam here. There was a fulcrum and we had two people, standing on that beam. Varying mass was the same masses. It doesn't really matter, but we made sure we drew our FBD. Now, when we're talking about something rotating, oftentimes students want to draw every force that they can think of, but that's not exactly what we want here, right? The thing that we're concerned about not rotating is the balance beam. So I'm not too concerned about like the forces acting on this person, right? Some students will say, well, there's an FG on the person and there's an FN on the person. They're equal and opposite. That's great. That's true. On the person, those forces are there. But the person is not the thing rotating, right? The beam is. So I'm going to worry about only the forces on the beam. Let's put that person back there. Let's go ahead and sketch the forces on the beam. So is there a gravity force on the beam? Certainly. At the axis of rotation, right in the middle of this uniform beam, there's a gravity force or a weight force acting there. This person pushes down on the beam with a force equal to their weight. We'll call it FG on the right side. This person pushes down on the board with a force of gravity or a force equal to their weight on the left side. One thing we're looking at here, though, folks, is if this whole thing is stationary, it's not rotating, it's not accelerating, we know that that means F net must be equal to 0 newtons. We know that net torque must be equal to 0 newtons times meters. Let's write our net force and net torque expressions. Net torque, let's see, axis of rotation is right there. I see torque from FGL going counterclockwise. Let's subtract it from the opposite direction, which is right side. Let's look at the net force. I see FG left, which is pointed down. Remember, forces aren't clockwise, counterclockwise. Forces are up, down, left, right, forward, backward. These forces are all down. So FGL is in the same direction as FG board, is in the same direction as FGR, but like, we're stuck. I need this to be equal to 0. There's no way I can add up three things of positive values and get to 0, so something's missing. There must be something missing. It's right here. There is a support force or a normal force, whatever you want to call it. You pick your name. It doesn't quite matter, but you pick a force. There must be some support force there in order for us to say minus F normal. Now the normal force is that opposing force holding everybody up. We don't need that here. It's not here. It's not causing rotation. It's at the axis of rotation, so we're good there. But remember, in order to balance things out, if something is going to be completely stationary, we need a net force equal to 0 and a net torque equal to 0. So use these, check these, and then honestly, folks, we can kind of substitute some things into other equations when we need to. After all this parallel stuff, we went ahead and we started putting things at an angle, saying like not all forces act perpendicular to lever arms. So we went ahead and we said, what if there was a wall and on that wall there was a sign, say a horizontal beam right here, and I hung a sign somewhere off the edge of it, and then there was a rope attached right there. What's happening now? Well, we went ahead and we drew our forces. We said there's a tension force right there. There's a tension force right here. I can call this tension force 1, tension force 2, which is equal to the FG of the box. There was the weight force of the beam. There's also, though, if we look at this, tension force is pulling somewhat horizontally. There needs to be an opposing horizontal force also from the wall pushing against. So we're going to go ahead and call this one a hinge force, F hinge X. At the wall, anytime a beam hits a wall, there are hinge forces. The wall is exerting some kind of normal force back on the beam, which is wild because I know that if there's a normal force back on the beam, there's going to also be a perpendicular friction force. I'm going to call it F hinge Y. This allows me to it could be any type of force. It doesn't necessarily need to be friction. It could be any kind of force, but at the hinge, there's always going to be a horizontal hinge force and a vertical hinge force. Let's call them F hinge X and F hinge Y. What we found out from this, though, as we went ahead and we wrote out our expressions, is that torque is not just equal to force times distance. away from the axis of rotation, which we'll put right there for now. What we ended up finding out was that there's a couple different things this thing could be equal to. It's like torque is equal to force perpendicular times r. It's equal to force times the perpendicular radius. And it also says somewhere like F r sine theta. Like, okay, we have these three different equations. What do these equations mean? What is this theta? And where do I find it? Is it radians? Is it like my kinematic equation? The answer is no. The answer is actually, in my opinion, a lot more simple. Basically, what it says is in order for the concept of torque, in order for something to rotate around an axis of rotation, there needs to be a force that is perpendicular, or at least somewhat perpendicular, to a lever arm. In this case, here is our axis of rotation. The rotating object, or the lever arm we're talking about, is the beam right here. Okay, I need forces that are somewhat perpendicular. I would say FG beam, totally perpendicular, which means the entire force will cause rotation. All right, F tension 2, perpendicular. That whole force will cause rotation. The tension force here, FT1, part of it is pulling the beam in this way. Part of it is acting perpendicularly this way, helping support the beam itself. It is the angle. This is what I tell my students. It is the angle. In order to use this equation here, when you've got a force that isn't perfectly perpendicular, theta is the angle between force and the lever arm. This is what it says. It's force times the distance that force is acting from the axis of rotation, and then the angle between them. If sine theta is if the angle is 90 degrees, then we know sine of 90 is 1, which means 100% of that force is going to cause a torque. If that angle is less than 90, well, then this number is going to get smaller and smaller and smaller until it approaches 0, which means if there's a force acted directly inward down my lever arm, sine of 0 degrees is 0. 0% of that force is going to cause any torque whatsoever. So this equation here, which is on your handy dandy equation sheet, is actually very helpful in not just understanding the math behind it, but also the concept of perpendicular forces to a lever arm. Use your equation sheet not just for math, but use it for concepts. Understand that this theta is the angle between both force and the lever arm. Okay. So we did a bunch of statics. We looked at objects that were stationary. We found that their net torques and net forces were equal to 0, all this fun stuff. And then we got things moving. And when things got moving, we did the same thing we did first semester. We started using kinematics. Okay. So let's go ahead and look at our kinematic equations from first semester. We said first semester, the very first equation we came up with was Vx, I think it's the way it shows up on your equation sheet, V initial plus AT. We also had change in x, initial velocity times time plus 1/2 AT squared. We had Vx squared equals V initial squared plus 2A delta x. And we had some relationships that we were able to build out from there. We had proportional relationships where V is proportional to T. That's what we got from here. V is proportional to T. We got X is proportional to T squared over here. And we've got V squared is proportional to X over here. These were all things that held true. Now, this is first semester. Second semester, we replaced these equations. We replaced them using angular variables. These relationships still hold true. We just changed their variables up. So instead of this equation, we ended up with omega final equals omega initial plus alpha times time. This tells me that omega is related to time in a linear fashion. Over here, delta theta equals omega initial plus t plus 1/2 alpha t squared. This means that theta is related to t squared. Now, these are proportionality statements. Don't get confused. These are not alphas. I call them Jesus fishes in my class, and I call acceleration alpha to distinguish between when I'm talking about the variable alpha and the symbol for proportional to. All right, these are proportionality statements. These are our equations. The last equation we said was omega squared equals omega initial squared plus 2 alpha times change in theta. And this told us that omega squared was proportional to theta. These were our proportionality statements. And then we went wild with these, solving a bunch of different equations, finding out that, and in my class, we used a paper towel roll, but basically finding out that a paper towel roll, as it rolls from one revolution around itself, leaves a trail behind it. That trail behind it is equal to delta x. Okay, well, it's also equal to the circumference, which is 2 pi r. We said that one revolution is equal to 2 pi radians, and that was called delta theta. It was our linear displacement. From this demonstration in class, we built out our bridge equations, the equations that link rotational motion to linear motion. This object was moving linearly while also, I'll call that v, while also moving angularly. What we saw was that delta x was equal to delta theta times r. And this became our first bridge equation. This expression is true. It's not on your equation sheet, but the concept right here, one revolution is delta x if it's rolling without slipping, and it is 2 pi r. So we take 2 pi, which is one revolution, times r. We end up with delta theta times r equals delta x. And then we said the same was true for all of our linear variables. Omega times r equals v. Alpha times r equals a. This is true only if you are rolling without slipping. And that is language you see on AP exams. Rolling without slipping. If you slip or slide on something, that means that this length leaving behind, or the length you're covering, delta x you're covering, is not matching the number of revolutions that you are making. Okay. This here also is a very important concept to understand. One revolution is 2 pi radians. This was our kinematics stuff. And then we went crazy and we linked all of this stuff together. We said, what if we linked all of this torque stuff with this kinematic stuff? What would that look like? And for us in our class, I think most classes did what we called a windmill lab, where you had some kind of pulley system being accelerated both linearly and rotationally by a hanging mass. So for us, we had this wild looking thing where there was a mass hanging from it. It had these crazy spokes on it like this, looking like some alien thing. This was behind here. Oh man, this thing looked crazy. And as this thing fell, because of the weight, we realized it wasn't necessarily falling in free fall, so there must have been a tension force pulling up on it. All right, we also realized there was something causing this thing to rotate and accelerate. Well, that must also be the tension force. This was our first lab. And this was the first time that we said, let's write a net torque and a net force expression. So we go ahead and do that. The only force acting in this case is Ft. So Ft times R. And folks, a lot of students forget this. A lot of students write T net equals Ft. Don't forget that torque is equal to Ft times R. Now it's rotating, it's accelerating, which means it's also equal to I alpha. F net is equal to all the forces acting in my system that are acting on it. Well, which of these is moving linearly, right? Like my windmill is not accelerating linearly, but my mass is. So this T net right here is of the windmill. And this here is of the hanging mass. And we'll see how these motions are so linked here in a second. So the forces acting on the hanging mass are Fg. It's going down. And again, I don't like changing my directions, I like changing my directions rather. Up is not always positive. Down is not always negative. I make sure that my acceleration is always positive. So whichever force or torque is winning, that is what direction of force or torque is winning. That's what I go ahead and make positive. So for us, I'm going to call this time clockwise positive and down positive. So Fg minus Ft is equal to the mass of the hanging mass, we'll call it mh, times alpha, or times acceleration. And this I right here is I of the windmill, okay? So we set this up. The one thing we want to make sure, the one kind of key that we got out of this lab in terms of variables is that the acceleration is very closely related to the angular acceleration. The same forces involved in causing this thing to speed up linearly are involved in causing it to rotate. So these motions are linked. We can actually substitute in A over R for alpha right here, and we did that a bunch of times. Now in my class, our job was to figure out, like, what is this? What is that value? So we went ahead and we graphed. We took data. That data was a bunch of different FGs, a bunch of different hanging masses. We measured the time it took to fall. And eventually what we came up with was our acceleration. We calculated the angular acceleration from linear acceleration, and we graphed this. In my class, I'm not sure what you all did, but in my class, we graphed the different torques over the accelerations. We got a linear relationship. And what we said was the slope of that graph was equal to the rotational inertia. In other classes, I know that you graph this, alpha and torque, because some people are going to say, well, Mr. Gustin, technically torque was the independent variable. I get that, but this one is easier to read for me because I'm not very smart. So I'm more excited to read torque over alpha because the slope is I. If you're reading alpha over torque, you'll still get that linear relationship. But folks, don't get confused. The slope of that graph is 1 over I. How do I know? I know because my equation sheet says this. My equation sheet says this. My equation sheet says alpha is equal to torque over I. And I think it says, like, it's got the sum, the sigma value. Okay? So when I do my algebra, I end up with I being equal to torque over alpha. So anytime I see torque over alpha, I know that is equal to my rotational inertia. So the slope of this graph is actually the inverse of rotational inertia, while the slope of the graph with torque on your y-axis is the rotational inertia of an object. That is a great question that pops up a lot of times on AP exams in May. Okay, so we had this bridging between linear and rotational. We had the outside torque causing rotation, but the outside net force causing acceleration. We write a T net for the objects rotating, and we write F nets for the objects moving linearly when they're accelerating. Okay, this was pretty much it, folks. We touched on static equilibrium. We touched on dynamic problems, things that are moving angularly and linearly. We touched on looking at the equations that were our kinematic equations. We touched on how to convert from a revolutions over into radians. We know how to bridge our variables from linear to rotational. I suppose the last thing we should talk about is rolling, because that was something that came up a lot. The thing that came up a lot was rolling, okay? So rolling, and I'm going to do a little experiment with you right now. Here's my axis of rotation, okay? I want you to tell me right now, think about it. The object here is on an incline. Do you know if the object is rolling up or down? I mean, I don't know, maybe not. Let's draw some forces. There's FG. I'm not asking for comments, right? I'm more asking like do a thought process, right? A thought experiment. Let's sketch some graphs or some forces right now. FG's down. Normal force is acting at the surfaces because that's the definition of normal force. Two surfaces meet. So surface, there's my normal force perpendicular to the surface. FG is down. Let's say it's rolling down the hill. All right, let's say it's rolling down the hill. So we have an angular speed of this direction. In your head, think about this. Think about this. Think about which direction must the net force, which direction should the torque be in to cause this thing to roll down the hill? In your head, right? Well, if this thing's going to roll down the hill, I need to see a torque that is acting clockwise up there. Okay? Is the normal force causing a torque? The answer is no. It's acting right down. It is acting like there's no angle between my force and my lever arm, no torque. How about this one? The weight force. The weight force acts at the axis of rotation. It's not at a distance. So no, Fg and Fn do not cause torque. Well, we're forgetting something. I think we're forgetting. Everyone forgets this equation. It's our fun equation. Our physics is fun equation. Everyone forgets that equation, but basically what it means is if there's a normal force present, folks, and we're not frictionless, there must be a force of friction. The force of friction is the only remaining force we have here. How do I know it's pointed upward? Well, I know it's pointed upward because not only is it moving in that direction, it's also accelerating in that direction. So the force of friction must be pointed upward. Folks, check it out. What if I do this whole thing all over again and I say now it's rolling this way? If it's rolling up a hill, it's still moving that way. It's still rotating. It's rotating counterclockwise now. Let's draw my forces. There's the weight force. Bam. There's the normal force. The question is there friction still? And which direction is it in? And this is something a lot of students struggle with, especially when it comes to lab formatives and that kind of thing. Which direction is the friction now? I know there's friction because there's a normal force. If there's a normal force, there must be a friction force. You have to ask yourself, where is it? Which direction is it accelerating in? It's rolling up the hill, but is it speeding up or is it slowing down? And I don't know about you, but anytime I've ever watched an object roll up a hill, it is slowing down. For some reason, it slows down. So that means the acceleration is opposite the direction of angular velocity. I still need a net torque in the clockwise direction. That means regardless of whether or not you are rolling up a hill or rolling down a hill, the force of static friction is always pointed up. That is different than when we're talking about the force of kinetic friction. Kinetic friction is always a resistive force, but static friction only exists when two objects are not slipping past each other. And as we already talked about, we are not going to be slipping if we are rolling. Folks, those are the big concepts from this unit. There aren't many. I see a question about, are there any, I see a question about, I see a lot of questions. I'm gonna back down. Who disliked? That's rude. You know, I get it. Physics is not everyone's cup of tea. Marcos, okay. Anyway, graphs to review. I mean, I hope I've impressed upon you all the similarity to first semester. So, I would say any of the graphs from first semester, right, our position and time graphs, our speed and time graphs, our acceleration time graphs, and those relationships all are the exact same for angular displacement, for angular velocity and for angular acceleration. So yes, the kinematics graphs are still very important, but there's no new concepts, right? Like there are very few new concepts. The only new concept really is this idea that torque equals I alpha, and what the heck is I even, okay? The whole idea of physics is mean to kids. Maybe you took the class. Actually, child abuse. Hey, folks, you don't have to be here. If you identify differences between FR sine theta, can you identify differences between FR sine 90 and F is perpendicular to R in regards to torque? There is no difference, right? That's the point I was trying to make, Samuel. FR sine 90 means that the force that is being applied to the lever arm is perfectly perpendicular to that lever arm. You can actually write this like FR, where F is perpendicular. I believe this is actually how it appears on your equation sheet. And so if this is 90, right? If sine is 90, all it means is that if we have a lever arm, say, for example, a seesaw, and that seesaw, axis of rotation, if there is a force acting down at 90 degrees, all of that force, let's say it's a weight force, all of that force causes a torque, okay? But if you and your buddies are out at the playground, hanging out, flashback to your elementary school days, and one of your buddies pushes like this at an angle, well, then that force does actually move it so that it's in the proper spot for an FBD right here. Well, now all of that force is not causing rotation. Only the perpendicular component is. So I'm only concerned about the perpendicular component. I'm only concerned about this force right here. Okay? And so the sine 90 comes from, if I go ahead and take the angle between my lever arm, or R, and the force being applied, that theta right there, that is the angle between that, and that's the theta you would be plugging into your FR sine theta equation. It's the angle between your lever arm and your force. It tells you what it is. It tells you right there. No problem, Sam. Couch, you want all the equations on my whiteboard? Dude, you got an equation sheet. Go highlight them. Rebecca, can you do a two-body? I did with the windmill, right? The windmill is a two-body problem where you've got, you're kind of writing a net torque expression for the object rotating angularly. You're writing a net force expression for the object accelerating linearly. And you're able to use typically, almost always, I would say in our class, I would say all the worksheets, 99% of the time, you're going to be substituting in acceleration over R, A over R. I'll write that one out. You almost always A over R in for alpha. It's almost always what you substitute in for two bodies, at least in our class, right? I'm not going to say like on every AP exam, that's not what I'm talking about, but I'm saying like in our class, this substitution into your net torque was pretty much how we always were able to do that. And the reason we have two equations is because oftentimes there are two unknowns. We're asked to solve like for angular or linear acceleration, and we don't happen to know like a tension value. And so we want to make sure we use both the net torque and the net force equation to do that. But if you go backward to the windmill lab, I kind of talked about two bodies before I talked about the graphs. So that should be there for you, Rebecca. What does it mean if an object is going down a ramp while slipping? It means it's like moonwalking down a ramp, right? If you're going to slide down an incline, that means that my bridge equations don't work. That means there's like force of kinetic friction, not force of static friction. In fact, I could say, honestly, I could be like, well, this box, if I've got a box on an incline and it slides down, I can be like, well, that box is rolling while sliding. Because like, is it rolling? No, but is it sliding? Yes. And if it slides, force of kinetic friction is upward. And if it does roll and slide, that means we're kind of going back and forth between this kinetic friction and the static friction. Basically, some crazy wonky physics is happening. And it's oftentimes only things that we would be asking you to think about conceptually, not necessarily about mathematically. So rolling while slipping means that there's kinetic friction there. And it also means that we're not going to have a torque, because if we have kinetic friction we don't have rolling. We need static friction to roll, because rolling is when the tire hits the ground, or the object hits the ground, sticks, and the center of mass tumbles over that point of contact. So sliding, slipping, it's weird, but basically what it means, no bridge equations. Can you please do a derivation problem where relating to using both torque equations? Trisha, if you go back to the windmill problem, I did it back there. Okay. I didn't go through the whole problem. I'm not doing that, right? I'm not really solving problems here. I'm helping you build connections so that tomorrow you understand how to build these connections in your head. All the practice problems, there are answer keys out there for you. Actually, there might be a video, if you go back to my channel, that has me doing a problem like that, perhaps. Otherwise, I know Mr. Boesday has one out there somewhere. How do you know where to put the axis of rotation when it asks you to place the axis of rotation? That's a fair question, Iman. Here's what I do, right? We know that the axis of rotation doesn't technically do anything for the physics. All it does is something for the math. So if I went ahead and said, like, looked at one of our seesaw problems like this, you know, and there's a weight force over here, you know, there's a weight force over here. There's the weight of the board right there. There's a normal force here, F support force. I don't know. For me personally, Iman, what I do is I always place the axis of rotation at the location that makes sense. And here, and you're going to be like, well, that doesn't help me, Mr. G. Here's what I mean. What I mean is, if this thing were to rotate, where would it rotate around? If this seesaw was going to rotate, where would it go? It's oftentimes called the fulcrum or the hinge or a balance point. But like, where would this thing rotate around? It would rotate around here. That's where I'd put that. Okay. Now it does something for me mathematically. What it does for me is it actually means that FG board and F support are not causing torques. Okay. So I'll write that out. Forces at the axis of rotation. I want to make this abundantly clear. So if you're still here, pause Netflix or whatever. But like, forces at the axis of rotation, oh my gosh, they are still there, right? They are still forces. They are still acting linearly. They are still either preventing or causing linear acceleration. They are still there. They are still doing everything that their force requires them to do, right? They are still in the forces club. But if they're at the axis of rotation, they do not cause torques, right? Like, they need to be perpendicular to a lever arm. Is there a lever arm at the axis of rotation? No. They can certainly cause this thing to accelerate up or down or stay stationary, but these forces will not open. Like, they will not cause the thing to rotate. I promise you. Go to your door, open the door handle, and have your brother push at the push right on the hinge. Push on the hinge, not on the door. Push right on the hinge, right on that door, on that fulcrum. It's not going to happen because you need some amount of lever arm. Okay, this is true. And the biggest mistake students make is think that forces at the axis of rotation do not cause torques or forces. Like, those forces are still there doing their force duties. They just aren't causing torques. Okay. So Iman, my answer to that is you put it somewhere that makes sense mathematically, but also if it's going to rotate, the fulcrum, the hinge, a balance point, that's almost always where you're going to be putting your axis of rotation. Also, a giveaway is kind of any force you don't know. Oftentimes that's a support force. You want to put it kind of right there, so that mathematically we can kind of cancel out some of those forces in our net torque expression. Why is it static friction instead of kinetic friction? Well, Nathaniel, if it's kinetic friction, we have sliding. If you are sliding, none of this rotation and none of this like bridging stuff works, right? We dealt with sliding all first semester. Boxes sliding down inclines. We slid a bunch of stuff down inclines. The reason that static friction produces rolling is because in order for something to roll, a new part of that object must touch the ground every instant. That means the object basically hit. Let me get my basketball. Ugh. Basically, Nathaniel, if I'm going to roll my basketball right here, Like watch the seam, right? This seam ends up back there. Does the seam slide? Is the seam sliding? No, the seam is here, and now the seam is back here. The object that touches the ground, the part of the object touching the ground, does not move when something rolls. If it slides, whoosh, kinetic friction. But because it is sticking to the surface, we have static friction. All right? I airballed it. Whoa, I just jumped around. Where did we go? Where was I? Nathaniel, there you are. If something is slipping, is its motion completely linear? Not necessarily, right? In the driveway today, I was backing the truck out, and I couldn't get my truck to drive. So I had slipping, but I didn't have any linear motion, right? I only had rotational motion. So the big takeaway from slipping is that we're unsure of what's happening. If we're slipping, it could be moving only rotationally and not linearly, or you could be moving linearly but not rotationally, right? Talk about like once my truck was moving, if I slammed the brakes, I'd slide to a stop. So no, slipping does not mean you're moving only linearly. Does torque always need to be associated with friction? No, Angie. Nope. I have torque here. I have no torque here. I mean, I got some forces that might produce a torque. None of them are friction. Now, if you're talking about rolling, does rolling torque have to be associated with friction? Yeah, it does. Can you explain why on number 2 in the review guide? I'm not certain I want to do review guide questions right now. I got questions in the chat, so maybe I'll come back to that if we get done before an hour here. If it is slipping, then how would you convert rotate? You can't, Manas. You can't. That was the whole point I made, right? If we're slipping, our bridging stuff doesn't work. I'd have to analyze it both linearly and angularly, but I would not be able to use my linear motion to help me understand my rotational motion. Tangential acceleration versus angular acceleration. I don't. Is Tavish? I'm not Tavish 27. Are you? Tell me right now in the chat. Are you referring to something on the review guide? Is Tavish still here? T-Vish 27. I guess I'll come back to that. Question from way earlier. Difference between tangential acceleration and angular. If you're talking about the review guide question, it's a silly question. I cross that question out every year. I tell my students to cross it out every year. I don't know. It's one of those old school physics things that some people think is necessary, but there's the difference between tangential acceleration, which would be like linear acceleration on a point that is away from perpendicular, speeding up. Meanwhile, we're also forget about it. Doesn't matter. It's not a concept that we're worried about. FGX. No, Sam. Gravity. If we are talking about rolling, the force of gravity does not cause a torque. Draw a picture. This is why I say I'm not here to give you answers about memorizing things. Where is the weight force acting? It's acting at the axis of rotation. So anybody saying to themselves like, well, yeah, that means that there's like an FGY and an FGX. No. Yes. I mean, yeah, for sure. Those forces are totally there, but FGX is acting right here. A torque, by definition, is a force acting perpendicular to a lever arm. Where is your lever arm? It's at the axis of rotation. It's at the center of mass. This will not cause rotation. It will not. Only, in this case, only the force of static friction. Yes, Sam, you're right about that. Any tips for derivations? Write out your equations. Keep plugging in variables. The only tips I have for derivations, and it may be helpful, maybe not, I don't know, is to get your expressions into what I call your base variables. Get them down into mass units. Get them down, like get mass in there, get R in there, get time in there. Anything that you can substitute in, attempt to do so. So I always tell my students that saying like a net torque expression for this, let's say for this one, T net equals FG left minus FG right. I'm sorry, torque of FGL minus torque of FG right is absolutely useless. unless you're given torque values. Like this equation here for a derivation, absolutely useless. I would even skip that and go right to FGL times RL minus FG R times R, right? Like get yourselves down, boiling down, right? And even FG, I tell my students, FG is useless, right? Go straight for mass of the left side times G times R of the left side minus MGRR. Right? Boil your equation down to base units, simple units like mass, and that's going to be 0. But that's my only advice for derivations. There's not really a whole lot of like advice like always do this, but like that for me has helped me. Can you explain why mass cancels out when comparing the speed of objects racing with the same mass density, but different masses? 1, 2, 3 skater, do you want me to just like show you that, or are you asking me like conceptually why? Because conceptually why, again, the fun equation, the equation everyone forgets about, right? Heavier objects mean more force of friction, right? And so the static friction, like something that is heavier will end up having, right, more friction. But when it comes down to it, like it's more enough to get it down the ramp at the same time. Yeah. So, but you don't need me to prove it to you. You do it yourself, man, or lady, or 1, 2, 3 skater person. You, right? Go plug it. Go go set up an equation, right? Go start here. T net equals I alpha. Improve that alpha for the big mass is equal. Or, sorry, prove that A for the big mass is equal to A for the little mass. If you can go prove that, then you got your answer right there for you. Why do people use F sup instead of FN? Sam, maybe they're just trying to say, "Hi, that's a terrible joke." I don't know. What you call a force doesn't matter. You're labeling it, right? As long as you're communicating something to the reader and the reader understands that communication, you're fine. So F sup means just support force, and FN means normal force. So, you know, both work. Both mean the same thing. Both are perpendicular to a surface. So, if we were driving an equation for net torque, Callista, you're asking me a question that I'm not sure, an incomplete question. What I mean by that is, if we're deriving an equation for net torque and force is on the center of rotation, should we not include it in the equation? Now, if we're talking about like a two-body system, Callista, or we're talking about an object that has both linear acceleration and rotational acceleration, if a force is acting at the axis of rotation, it will not cause a torque. That is true. But it's still doing all things force related. So if I'm going to write an F net expression, yeah, it needs to be there. It's still a force. It's just not causing a torque. Forces don't go away because they're at the axis of rotation. They simply don't cause a torque, but they are still there doing all forcey things. What are the coefficients of an inertia equation supposed to represent? Their mass distribution, Angie. The coefficient indicates how near or far the average mass of an object is located to the axis of rotation. That is why a hoop, like a hula hoop, has a coefficient of 1, because 100% of its mass is located at the maximum radius. Now, it's not necessarily like a linear relationship where as the mass gets closer, that coefficient decreases at a linear rate. It's based on a definite integral, kind of solving for the volume of the shape and the mass density of the shape. So it's a calculus thing. I will give you any coefficients you need. Maybe I'll ask you to solve for a coefficient, but the concept, what's more important is the concept of mass distribution. If more mass is located further from the axis of rotation, you have a higher I value. And if mass is located nearer the axis of rotation, you have a smaller I value. Yes, TVish 27. So the coefficient is closer to 1. That means it's going to be harder to rotate. Yes, it is more angular inertia, rotational inertia. How do we know when there are hinge forces? If there's a hinge, Caroline, if there's an object touching a surface, yeah, if there's a hinge, right? Like a sine problem, those kind of things, there'd be hinge forces. Can you explain the rotational inertia lab? I believe I did, Manasvi, go back. I talked about the windmill lab a while ago. Yes, Tivish, you said it's a repetitive idea, so I assumed it was a concept. Yes, mass distribution is a giant concept. You can go back and look at your windmill labs and see how the different what windmill setups produced different slope values. So for objects that had more mass distributed, with the masses further down the prongs, had increased slopes or higher I's. And as we brought those masses close to the axis of rotation, that slope dropped down. Ezra, I just talked about that a little bit ago. How will the test work? That's a teacher for your, Michael, that's a question for your teacher. If two solid spheres roll down a ramp and the only difference is their mass, how do you know which one is greater acceleration? They should have the same acceleration, Alex, in terms of two solid spheres, different masses, like just different densities straight up, like same radius, that kind of stuff. Yeah. Yes, they will hit the bottom. Because like I said earlier, they'll have the heavier one will have a larger torque value. Even though its I value, the coefficient for the I's will be the same. Its I value will be increased because it has more mass, but it will also have more torque because we know that the normal force ends up producing that friction force. So more normal force means more friction force. Therefore, as yes, it's heavier, so it has a higher I value. It will also have a higher torque value, meaning that the acceleration of the heavier object will still keep up with the smaller object. How do we know when our T-net equation is equal to 0? So it's only equal to 0 if the thing is not accelerating, or it's not angularly accelerating. Sorry, it is equal to 0 if it's at rest, or if it's at a constant speed angularly. That's when T-net equals 0. All right, very similar to forces. Any question you have, try to replace that question with linear vocab words. So when is torque equal to 0? When's force equal to 0? When the forces are balanced. When's torque equal to 0? When the torques are balanced. When is that going to happen? If something's at rest or if something is not angularly accelerating. 1, 2, 3 skater. I don't believe there's a class kick going on. I don't know. I don't run the class kicks usually because I'm here. T-net is equal to 0. Yep. Yes, Christian, that's correct. But also it is equal to 0 if we're not accelerating rotationally. Callista, got it. But what about a torque equation? No. Callista, back to your question from earlier. No. If there is a force acting at the axis of rotation, it will not be included in your torque value. Marco, yeah, I didn't break them, Marcos. I just cut them out briefly. What torque allows an object to roll up a ramp? Whoa, Simon, hold up. Torque is all about rotational acceleration, just like force is all about angular acceleration. If I have an object that slides up a ramp, there's not necessarily a force causing it to slide up the ramp, right? Maybe I gave it a shove and its mass is carrying it up. Its inertia is carrying it up the ramp, but the force of gravity in the parallel direction is pulling the box, sliding it back downward. Now, when it comes to rolling, maybe it's, someone kicked it and it's rolling, or someone, pushed it and it's rolling. Its inertia, its tendency to maintain its speed or its motion is causing it to roll up the ramp, but it's going to slow down if it rolls up a ramp. The question is, what torque causes it to slow down while it rolls up a ramp? That is the torque question. We should not be asking what causes it to move because its inertia causes it to move. We should be asking what causes it to accelerate rotationally. That's torque, and that's the force of static friction producing that acceleration in the, well, it depends, but basically down the ramp. Stella, correct. No class kick. Only sometimes. I don't know what that means, Marcos. Sometimes, yeah. Folks, that's an hour right there. I reached the bottom of the chat. There should be a key posted for my students. I've been getting emails. It's saying it's not posted. I will double check. So I'll go make sure our unit 6A review guide is posted out there. For my class, lab formatives are due before the test tomorrow. I'll see you all in seminar, unless you've got more questions. Seminar will just be hanging out. You'll be wrapping things up. I won't do any instructing pretty much. I won't really answer any questions. I'll just tell you to come here and watch this on 6 times speed. But hopefully you're all prepared when you show up to seminar tomorrow for your test during 6th or 7th hour. Ezra says, if you have an object like a tree where the R is different in vertical and horizontal directions, how would you find rotational inertia? Wow. Ezra, I don't know what you mean. If you have an object like a tree where R is different in vertical and horizontal. I got it, Ezra. So Ezra, this is going to be this. If you're good, the answer to Ezra's question is super nerdy. So if you're going to nerd out with us for 30 seconds, that's awesome. If not, get out of here. Have a good luck on your test tomorrow. You all will do fantastic. When you get stuck, replace your rotational questions with linear vocab words. When you're stuck on torque, replace it with force. When you're stuck on angular acceleration, replace it with V. That replacement, those concepts are all the same. You'll be fine. Do not make flashcards. Just remember that connection. Lab formative 4, I don't know. 1, 2, 3 skater. I don't know whose class you're in. Okay. All right, let's geek out here for a second, Ezra. Technically speaking, the reason I say you have to use calculus, anytime we have like many options or many points, a tree is weird. A tree, let's call the base of that tree the axis of rotation, like its trunk, in case it's going to tip over like in the wind. So the tree is the axis of rotation. Now, to find the rotational inertia of that tree, what we actually have to do is technically take the infinite sum, because it's made up of particles, but those particles are pretty much in an infinite in number, right? There's a lot of particles in there, a number so big, it's hard to even figure out. So we will take the rotational inertia. We can calculate the rotational inertia, the mr squared of all the points, all the pieces of matter inside that tree, and add them together. So every point, every single point has a rotational inertia value equal to mr squared. That's true. But a tree is an interesting shape because they're different shapes. So what we'll do is we'll use calculus to say, here is a very exact approximation for all of the points in that tree. We'll use calculus. We'll solve a definite integral, which is a sum problem, basically summing up all of the rotational inertias. And we'll end up with a value that tells us the rotational inertia for the tree. It won't tell us a coefficient, but it will tell us the value for the rotational inertia of that tree. So Ezra, that's true for any object, any strange object. What we will do is take the infinite sum. If you're familiar with limits, we can take the limit as it approaches infinity. So we'll take the limit as it approaches infinity of the rotational inertia of all the particles in that tree, sum them up, and that's a rotational inertia. That's super nerdy. I'm sorry. It's Sunday night at 8 o'clock, and we just geeked out on that. So great question, Ezra. A more complicated question than probably physics 1 will ever ask you to do conceptually, but still a super cool question. Essentially, the answer is they all have got mass values and they all have got R values. We just have to find them and add them together. Oh, well, that's more straightforward, Ezra. If the question talks about the short tree and the long tree, which one's got more rotational inertia, right? If they're the same mass, which one's going to have more rotational inertia? The one with the longer lever arm or the one with the shorter lever arm? When a board has 2 supports. Yes. What about that? 1, 2, 3 skater? When a board has 2 supports. A board can have 2 supports. A board will only have 1 fulcrum, though. So that's a question that happens a lot. I think on a lot of worksheets, it's like a diver problem. Hang on. When a board has 2 supports on either side of a person, when a board has 2 supports on either side and a person stands on the right side. So like a scaffold, basically, a scaffold like this and looks something like this. There's a board across it. A person is standing on the right side like this. And why does the normal force from the left side not exist? Well, again, like I mentioned earlier to someone, I believe it was Iman, I think I'd mentioned too. If I'm trying to place an axis of rotation, let's think about where the axis of rotation will be. Like, where's the fulcrum? If this thing were going to rotate, if this person were to start walking this way on the scaffold, at what point will stay fixed and what parts will move? Well, that's right here, right? Like this part of the system will be my fulcrum. As the person walks this way, eventually that board's going to tip and this force is going to go up. So at the point when the person is at their furthest, right as this person gets to the furthest point they can out here before it tips, this board here is going to slightly lift off of its support force. And so that means that Fn is equal to 0 newtons. So as they go further and further, Fn gets smaller and smaller. And right before they, take the nosedive off the edge of this board, Fn is exactly equal to 0. Big man Mimi, thank you. Got to check my remind. I get texts from students on remind. They're asking to post the key, which means I got to get out of here very shortly. It's been over an hour. I did, Couch. I did. I switched to AT&T, and I regret every second of it. But yes, Couch, you are right. You making fun of my phone, Couch? Okay, good. All right, folks. That's it. Rewind. Go watch it. Go check your keys. I'm getting out of here. Good luck tomorrow. You all do fantastic. Just remember, this is simply first semester with different vocab words. All right? See ya!